Alright, so we're going to begin part 2 here with a discussion of formal charges. Alright, so the simplest illustration of this is the molecule ammonium chloride, which you've probably known for a long time is an ionic compound that's NH4 plus, okay, right here, and Cl minus. Okay. So let's look at how the charges distribute in ammonium chloride. Okay, when we do the Lewis structures, one of the things you probably realized is that when we have a lone pair, the atom owns both of the electrons, that is, the atom that it's attached to. However, when we have a bond, these electrons are shared between two atoms, so we can say that the atom that we're looking at owns half of the electrons in that bond. Okay, so we can look at the charge distribution by, or the formal charge, just by working this equation for each atom. Okay, we're going to take the number of valence electrons in the free atom, subtract that from that the number of bonds, and subtract from that the number of electrons in lone pairs. Okay, so let's look at the atoms in ammonium chloride. So for the nitrogen in ammonium chloride, it's got 3 bonds in it. Sorry, 4 bonds at nitrogen. And we can say that the formal charge at nitrogen, there's 5 electrons in a free nitrogen atom. Okay, it's got 4 bonds, and there are no lone pairs at nitrogen, so when we do this equation, the answer comes out to be positive 1. For chlorine, chloride ion, there's 7 valence electrons in the free atom. There are no bonds to chloride, and there are 8 electrons. Okay, so 7 minus 8 is negative 1. We say that the formal charge there is minus. Okay, so we would write this symbol right here to symbolize that there's a formal charge at that nitrogen. Okay, so this is an abnormal nitrogen. Our normal nitrogen would have 3 bonds and a lone pair. So when it has 4 bonds and no lone pairs, it has a positive charge. Okay, I can't emphasize enough that not everybody agrees that formal charges should even be discussed, but it's a very useful bookkeeping device for telling you where the electrons are. The main argument here is that formal charge doesn't really take into account the electronegativity differences. Okay, so when it comes to ammonium chloride, there's really no formal charge, or there's really technically no net charge at nitrogen, because even though we're showing a formal charge of plus, the fact that the hydrogens are less electronegative than the nitrogen means that electron density is being forced to nitrogen. Okay, so all the molecular dipoles kind of dump electron density at nitrogen, so this tends to counterbalance it. But we're going to use formal charges quite heavily in organic chemistry because it sort of tells us the number of lone pairs and bonds that we should expect for that particular atom. So it's a vital bookkeeping device. Okay, let's do first, before we go to actually calculating a few sample formal charges, let's just look at elements in their normal valence state. If I told you on an exam to calculate the formal charges in a kind of a large molecule, you could do it for every one of them, but in your average molecule, most of the atoms don't have a formal charge. Okay, this is because they look the way they normally should, to have no charge at all. Okay, so this chart here just tells us what is the normal valency for various elements. So hydrogen, the normal valency is to have a bond and no lone pairs. Boron and all the elements beneath it, like aluminum and gallium, they should have 3 bonds and no lone pairs. Okay, boron does not have an octet, and we'll get into that sort of later in this chapter with a concept called Lewis acidity. Okay, carbon should have 4 bonds, no lone pairs. Nitrogen and phosphorus should have 3 bonds and 1 lone pair. Oxygen and sulfur should have 2 and 2. And the halogens should have 1 bond and 3 lone pairs. So when we have this situation, these elements do not have a formal charge. And so you know that you should not waste your time doing a formal charge calculation when one of these atoms appears with this arrangement of bonds and lone pairs. Okay, so let's look at this problem here. Where are the formal charges and what is the overall charge? And note that in this case I have shown every one of the lone pairs. Okay, alright, so in magenta here I have outlined all of the elements that don't have formal charges. This is these represent elements in their normal state of valency. Okay, so all carbons with 4 bonds, all nitrogens with 3 bonds and a lone pair, all halogens with 1 bond and 3 lone pairs, all oxygens with 2 bonds and 2 lone pairs have been identified. We can follow that phosphorus and sulfur are just like nitrogen and oxygen, respectively. Alright, so we're not going to waste our time doing any sort of formal charge calculation with those particular atoms. Alright, so here is our first formal charge. It's a carbon with 3 bonds and no lone pairs. Our formal charge there is +1. Okay? And by the way, this is about as difficult as the math gets in organic chemistry. If you're expecting a mathematical experience in this class, you're going to be a little bit disappointed. Okay, right here. Here's another element that's not in its normal valency arrangement. Our formal charge here is just like ammonium chloride. There's 4 bonds and no lone pairs, and when you subtract out the normal valence level of nitrogen, that comes out to be +1. Okay, this nitrogen right here has 2 bonds and 2 lone pairs. Its formal charge when you go through the calculation ends up being -1. Okay, and the last formal charge is its sulfur. Here, formal charge is 6 minus 3 minus 2, and it's +1. Okay, so these are our formal charges. What is our overall charge on this molecule? Well, it's +2. Okay, we have 3 positive formal charges and 1 negative formal charge, so they don't counterbalance each other completely, so this is a charged molecule. Okay, just like to say, it's conventional to omit the lone pairs and infer that they're either there or not there by the number of bonds and the formal charge that's indicated at each atom. In the early stages of this class, I realized that all of this stuff might be a little confusing at first. We're going to show you the lone pairs all the way up to exam 1, and if we're not showing you the lone pairs, we're warning you that that we're not doing that. But this is the normal convention to not show the lone pairs, and we infer their existence from the number of bonds and the formal charge if it is present. Okay. Alright, so here's a problem. You should pause the video and go through this problem. Assign all the formal charges in this molecule. Notice that so as to make this drawing a little bit less messy, I didn't draw the lone pairs at fluorine. Each fluorine has 3 lone pairs. They're just not shown. Okay, So as we do this, we want to find out what atoms do we need to actually do a formal charge calculation on, and you'll find that you don't need to do them on fluorine, and you don't need to do it on this oxygen right here, which I've asterisked. Okay, but all the boron, the nitrogen, and the other oxygen are all not in their normal valency, so we have to do a formal charge calculation. Okay, so this oxygen right here has a net charge of +1, 6 minus 3 bonds minus 2 lone pair electrons. The nitrogen also has 4 bonds, and its charge is +1. The boron has 3 is the valence electron count. It's got 4 bonds and no lone pairs, so it ends up being -1. There's no other atoms with a charge, thus the overall charge on this molecule is +1. Okay? Alright, so this is how we might want to write it with its formal charges and overall net charge indicated. I seriously doubt this molecule would be stable. It has 2 positive charges right beside each other, but this is primarily just an exercise in formal charge calculation. Okay, let's look at another topic here, that, and this concerns how we present structures in organic chemistry. The early organic chemists, when they were writing their papers and communicating to each other in print as to what they had found, would have to use a typewriter just like everybody else writing manuscripts at that time. Okay, so we developed a method of writing structures called condensed structural formulas. Alright, so this simple molecule here, fluoromethane, if written as a condensed structural formula, is just CH3F. This tells us that the carbon is bound to 3 hydrogens and a fluorine. It's a little bit confusing at first because it implies that the hydrogen is between the fluorine and the carbon, but that's not really what this means at all. I know it looks that way, but you have to just understand that we're just looking at the sum total of what's around carbon. Okay, this molecule here, ethane, is written as CH3 with no spaces anywhere in the molecule. Alright, let's look at the next molecule. It's a much larger molecule called butane. And butane has 4 carbons in a row in it. And there's a couple of ways we could write this as a condensed structural formula. One would just be to write each carbon as either a CH3 or a CH2 in a continual string, like we see here. Sometimes even that gets to be too long, and you would see, like, we would abbreviate it as 2 CH2 groups in succession, followed by a CH3. Okay, and this top one, this is ethanol. Okay, as a condensed structural formula. We just write it this way, CH3, CH2OH. The oxygen is just a continual part of the string. Okay, sometimes even the condensed structural formula is a little bit too long, and we go to something that's even more convenient. This is called Bond-Line diagrams. At first this is confusing to you because not all of the elements are shown, but you have to get used to viewing structures in this way because this is how they're represented. Okay? If you get a prescription and you open it, you'll see some sort of bond-line diagrams for the organic chemical you're about to ingest. All right, so this molecule here, I'm going to go to the one on the right because this is the one you've more than likely seen. This is benzene. Okay. Very famous molecule. Okay, so it has alternating double and single bonds, and each carbon has a single hydrogen at it. When this is represented as a bond line diagram, it is abbreviated just as a hexagon with alternating single and double bonds. Okay, it doesn't have to just be this beautiful hexagonal structure here. We can abbreviate any molecule that has carbon chains in it using this bond line diagram notation here. So this is cyclopentane. It contains 5 carbons in a ring. And its official bond line diagram is merely just a pentagon. Okay, so here are the rules for bond line diagrams. Each carbon atom is at the end of a line or the intersection of 2 or more lines. Okay, so here's some intersections right here. And each of those represents a carbon atom. Same over here. I won't do all of them, we'll just do a couple of them. Okay, the hydrogen atoms that are bonded to carbon are not shown in the bond line diagram. We're going to assume that there are enough hydrogens present to make 4 bonds to carbon. The only exception here would be unless a formal charge is indicated. Okay, we have to show all heteroatoms. Heteroatom means that it's means that it's an atom that's not carbon or hydrogen, but in most cases the heteroatoms are nitrogen and oxygen and the elements underneath them. Any hydrogens that are bonded to a heteroatom have to be shown. Okay, we don't always conform to these rules. For example, if we need it for emphasis, we want to show a reaction happening at a specific carbon, we might draw the molecule differently. So for example, if we wanted to show a reaction at the top carbon in cyclopentane, we could just draw it that way, and that would emphasize that something interesting is going to happen to that carbon. Okay, that's not a hard and fast rule, but we often do employ that technique for emphasis. Okay, the last 2 points here are just advice. They're not hard and fast rules. I say, do not use bond line diagrams for extremely simple molecules. For one thing, it's not such an onerous task to just draw the hydrogens for those molecules, and you'll it's just a better presentation when you can draw the hydrogens, but some molecules are so complex that you can't. So if it's really simple, just go ahead and not use a bond line diagram. The other advice that I'm going to give you is don't use bond line diagrams for charged carbons. They lead to a lot of confusion. I just, when I'm showing a charged carbon, I always draw all of the hydrogens at that particular carbon. Okay, so let's look at some examples of bond line diagrams. So the top compound, I just made it up. You could probably make it, I assume, but I don't know that it has any useful function. But if we turn this into a bond line diagram, we get the structure immediately over here. All right, what does the structure mean? Well, here's the end of a line. We only see one bond. Thus, there are 3 hydrogens at that carbon. All right, here we see 4 bonds to that carbon. Thus, there are no hydrogens there. Okay, here we see 3 bonds depicted. Thus, there is 1 hydrogen. Okay, notice that the hydrogen that's on oxygen has in fact been shown in the bond line diagram. Okay. All right, so let's take the illegal drug ecstasy, shown here on the left. Okay, when it's condensed to a bond line diagram, is this structure right here. Okay. Notice the 1 hydrogen that's on nitrogen is shown, but the rest of the molecule is shown as a bond line diagram. Okay, this is LSD, or lysergic acid diethylamide, down here, and its structure is a lot more complex, but this is the structure of LSD. Okay, I have here in this box some things that you probably shouldn't do, okay? And these are ridiculously simple molecules that you would never want to show as a bond line diagram anyway. So, ethane. So, just draw a line on a piece of paper to represent ethane. People are going to wonder, is that a dash? Or so never draw ethylene or ethane or a 2-carbon molecule as a bond line diagram. This next molecule here, methanol, again is a bond line diagram. It looks like that, but people just wonder, is that an OH with a dash mark, or is it OH minus? No, you wouldn't draw something so simple like that as a bond line diagram. Finally, I guess technically, if you just draw a dot, you've drawn methane. So nobody would ever draw methane that way. Okay, so bond line diagrams are for when the structure becomes so complex that it's inconvenient to draw all of the atoms anymore. Okay, so here's a problem for you. Pause the video and work through this problem for yourself. Okay, so this is the molecule Viagra, originally, I guess, developed by Pfizer pharmaceutical company as a treatment for blood pressure. However, it had side effects that were far more marketable than the original intention. So this has been a kind of a blockbuster drug for Pfizer Pharmaceuticals. What's its molecular formula? To do this, you're going to have to look at the bond line diagram, and imagine where all the carbons and all the hydrogens are in this molecule, because they're not specifically depicted. You can see all the nitrogens and sulfurs and oxygens, but you're going to have to infer the existence of carbons and hydrogens from the rules for drawing bond line diagrams. Okay, so all the asterisks here are carbons that have not been shown. They're part of the bond line diagrams. Okay, and if you look at specific carbons, you can find that here we have 3 hydrogens. Here we have 1 hydrogen. None there. None there. Hydrogen here. Hydrogen here. hydrogen here, 2 hydrogens here because there's 2 bonds, and thus the remainder have to be bond lines, or have to be hydrogens. 3 hydrogens are there. 3 hydrogens are here. 2 hydrogens, 2 hydrogens, 2 hydrogens, and 2 hydrogens. Okay, when you add it all up, I believe the formula is C19H24N6O4S. So I'm going to pause, or I'm going to cut this video off right here, and the rest of the stuff in this chapter is going to be presented in 2 additional videos. Okay? Alright, so we're going to end the show.